we want to think about, well, we have P, pressure times volume is some constant times T. Let's think about getting this, as we said, from some notion that we're dealing with little objects that collide. So without being too precise about this, there really are some assumptions here, but we'll have little particles, or let's just call them molecules, moving around with some speeds, ultimately in random directions. And let's see if we can recover this kind of thing. So we consider a little particle. It has some mass, m, and it has some speed. Let's say we're thinking of speeds left and right. So this object, this little particle, travels a certain distance. It'll be some distance x. It hits the wall and comes back. Let's say something like that. And it has some speed. Let's call it some, I don't know, vi. Well, maybe we should call it if we're going to consider horizontal, let's call it a Vx. And so it starts here, travels a distance x, it comes back here. There is a change in momentum. So there is a delta P that we need to consider. And that delta P is, where in magnitude, we're dealing with, well, final minus initial. So we have something like m Vx minus minus m Vx, and that's a minus 2m Vx. And of course, if we want a force concept, we have to consider the interval of time of which that happened. That's really, this is the difference in momentum, and over the time that occurred, that's sort of the average momentum change or force. So we would have something like, in terms of magnitudes, we would have a force which is just delta P over delta T, over the time it took for that to happen, for the particle to travel x this way, hit the wall, come back, and travel a distance x that way. And so here we have a, sorry, this is a plus right here. So we have a 2m Vx over delta T. Because of the speed, then we have x and then x again, so that's a distance 2x, and that distance was covered at this speed Vx. And so we know how to relate delta T to these quantities. And so we can say that delta T is equal to 2x over Vx. And so F is equal to, which is 2m Vx over delta T. We can then say that this is equal to 2m, we'll divide this by the 2x, and then we have the Vx, so we have a Vx squared here. So what we see is something that looks like a kinetic energy, mvx squared over 2. So this is the force of one particle. So let's consider a whole bunch of little particles or molecules. And so we can think of adding these kinds of things, adding these F's, Fi's. And so that gives us a sum of m Vx squared over x quantity. We can pull out the m over this distance, and we're summing over this Vx squared. we also know that if we take this sum, if we consider this term, so we're summing over that, so we sum over these horizontal components of velocity, square components, and we'd say we have n. Let's now introduce another number. N is the number of little balls that we have, or molecules, and we divide that by n. Then we have the average of this squared horizontal velocity. All right, so that looks like that, and so we can write our force as m over this distance. So we're going to replace this with this times that. So we have an n times this average of Vx squared. And then we can consider motions in other directions, right? So there's a certain symmetry here where we have a box. So we would say that this quantity is the same in all directions. So if we have a Vy squared average and a Vz squared average, that would be V squared average. And so if these are all the same, we have three. Let's just use Vx squared average. That is equal to V squared average. And so we can say that the force is equal to n, the number of molecules, divided by 3 times m times the average of this V squared over this distance traveled, x. And so now we can look at pressure and find how to relate the speeds and the masses of the n molecules to the pressure, which is a macroscopic quantity. And pressure but so is force. So, but we're trying to determine this macroscopic quantity. And so we can say that pressure is equal to force over area. That means we have force over, all right, so we're thinking of these distances x, and then they're the same in all directions because of the symmetry, so we can say our area is an x squared quantity. And so we have an n over 3 times this m V squared average over, we divide by x squared, so now we have an x cubed, and so we have 1/3 n, but this is a volume, so we can bring that there. That's a volume n over v, so we have this quantity, we have this quantity, and then we have v squared average. And so if we want to turn this into a kinetic energy, we have to again divide by 2, and so that means that we have the total pressure is, the pressure on one of the walls is 2/3 n over v times m, the average of v squared over 2. And so we have that the pressure is proportional to the number of molecules and molecules, and proportional to the average kinetic energy of those molecules. And the next step will be to try to understand temperature, so basically figuring out what this constant T, C is as well in relation to these quantities. So here we have so let's sort of conclude here, P times V is equal to 2/3 N times this K average. Okay, so this average kinetic energy needs to be something that's proportional to the temperature. Yeah, we conclude that kind of a thing.